let's get started. So today I'm going to talk about the correlation and the simple regression. So when we have the two variables, so we are interested in the two continuous variables. We are interested in the correlation between two variables, which means that when one variable increases and what's going to happen for the another variable increases or decreases. So we would like to want to look at the relationship between two variables. That's the correlation. And then when you have the outcome, so you have two continuous variables, and when you have the outcome, then so you have a dependent variable, and then when you have the predictor, and then we would like to see that how the change of predictor affects the change of the response. So that's the regression. So here we are going to, by looking at the correlation and regression, we can answer on these topics. So by using SAS, we would like to learn about to compute the Pearson correlation coefficient between two random variables. And then we would like to test the significance of correlation coefficient and the interpretation. And then we would like to learn how to use SAS to estimate the regression equation from the simple linear regression. So when I say simple linear regression, we have only one predictor. And then we would like to see how to interpret it and how to test the significance of regression coefficients. So the Pearson correlation is the definition of the, by Wikipedia, it says a measure of the strength of direction of linear relationship between two random variables. So Pearson correlation coefficient is defined as the population covariance divided by the population standard deviation of the x and population standard deviation of y. And then we can estimate the population Pearson correlation coefficient by the sample correlation coefficient, which is we denote as R. Which is we replace this population covariance by the sample covariance, and then population standard deviation of x and population standard deviation y by sample standard deviation of x and sample standard deviation of y. So we have this relationship. And then by using the graph, so this Pearson correlation coefficient, we would like to look at the linear relationship in here. So if here we have if we have this line, the linear line here, the size of the intercept doesn't matter. So we have if they have the exactly linear relationship, so then it's gonna be 1. Then if the linear relationship is not so in this 0.8 case, so in this case we have linear relationship, but we have the scattered the points, and the 0.4 we have more scattered points. And then if we have the circle, then we have no linear relationship, so we have 0. And then this is when the case the x increases and y increases. And then now we have x increases, y decreases. Then if we have perfect linear relationship, then we have -1. And then so here it doesn't, the size of slope doesn't matter. So if they have linear relationship regardless of the size of magnitude of slope, then we have this Pearson correlation equal to 1, or if for opposite sign we have -1. And then if we do not have linear relationship, then we have the 0 on here. So notice that for this case, we still have relationship, but it's non-linear. So this Pearson correlation coefficient does not capture non-linear relationship, so only capture linear relationship. So if you have variable, and then if you calculate estimate the Pearson correlation coefficient, and you say it's 0. If suppose it's 0, or you by doing the hypothesis testing is not significant, they're different from 0. So you say, oh, there's no relationship. Then if you say that, it's wrong. It's incorrect. So they may have the nonlinear relationship. So so just you looking at the Pearson correlation coefficient, and if you just say they have no relationship, that's not the correct statement. Thus in here, we have the Proxio RR, that computes the Pearson correlation coefficients or other non-proprietary measures of association, and the probability is associated with these statistics. So it computes the Pearson correlation product moment correlation, which is the Pearson correlation coefficient, and then Spearman's rank order correlation, which is the Pearson correlation between rank of two variables. So it's more robust than the Pearson correlation coefficient because it uses the rank. And then the Kendall's tau B coefficient, which is the number of concordance and disconcordance in paired observations. And the Hoeffding's the measure of dependence. And then partial correlation. So the partial correlation is so if you have more than two variables, so let's say you have a third variable, then you want to look at the correlation between first and second variable by controlling the third variable. So that's the case we use. When you look at the correlation between the first two variables by controlling the third variable, that's called the partial correlation. So it also gives the partial correlation, Pearson's, Spearman, and Kendall. And then the default correlation coefficient includes the descriptive statistics and the partial correlation statistic. And then for Pearson or the Spearman correlation, so we discussed it in the homework. So that there is a Fisher's Z transformation can be used to compute these confidence intervals. And the p-value under the null hypothesis is that rho equal to rho 0. So rho 0 is the specified value of the correlation. So it gives either two-sided or one-sided alternative. And then by default, the SAS tests whether the correlation is equal to 0. So this rho 0 is 0. So by default we are testing whether correlation is 0 or not. So if the p-value is less than 0.05, we reject the null hypothesis, which means that the correlation is significantly different from 0. And then if p-value is greater than 0.05, then we said the correlation is not significantly different from the 0. So simple syntax of Proxio RR is this. So Proxio are an options, and the by variable, and the partial variable, and the width. So this by variable specifies groups to compute the separate correlation analysis. So if you have, let's say, two groups, say gender, so then this partial, if you specify by with gender, then you compute the correlation by male and female. And then the partial statement identifies the controlling variables to compute the Pearson, Spearman, and then Kendall partial correlation coefficient. So this is the partials, and this, when you specify the third variable, then you compute the partial correlation of first and second variable that you specified, and then the controlling effect of the third variable. And then the VR statement is the you specify the variables for which you want to compute the correlation. So if you omit this VR statement, then so you ask SAS to compute the correlation or for all pairwise the numeric variables. And the width statement is the list the numeric variables with which correlations are to be computed. So let's look at the high school grade dataset again, and then we have 5 numeric variables in here. So reading, writing, math, science, and social study. And if you specify the correlation by these 5 the variables with using the VR statement, then you compute the So correlation of the five variables. So we have the so first we have the descriptive statistic, so mean, standard deviation, sum, minimum, and maximum for each variable. And then so we compute this correlation on here. So this first row, so the is the Pearson's correlation coefficient. So read and read the Pearson correlation, they are the same variable, so we have one. And then so this is read and write, and read and math, and read and science, and read and social study. And then here we have the same value as write and read because the Pearson correlation coefficient does not change even though you switch the order of two variable. So you can only look at the upper diagonal or the lower diagonal part. And we have the p-values on the second row on each cell. So for example, if read and write, so it says the p-value is less than 0.05, means that read and write, their correlation is significantly different from 0. And then this 200 is the number of sample size. So here we have missing value in this science. So we have the 199 observations for computing the correlation between write and science. So we want to ask the question, how large a correlation coefficient do I need to believe that two variables are correlated? So how significant my population correlation coefficient is. So that's so you can do this hypothesis testing. So this hypothesis testing, as I said, the read and write case, your p-value is less than 0.05, so it's the significant, there's correlation, population correlation coefficient is significantly different from 0 throughout the hypothesis testing, the rho equal to 0. So just some remarks. So the significance of correlation is a function of the magnitude of correlation and sample size. So as you said, if the magnitude is very large, so for example, if you have say 0.9, then you can think that they are significantly different from 0. So if the greater magnitude, then it is the correlation which will be significantly different from 0, that chance would be higher. And if sample size is large, then even though you have very small correlation coefficient, and with this very large sample size, then it would be the significant. So this graph shows the minimum value of the sample size and Pearson correlation to be significantly different from 0 at the 0.05 level. So you can see that for smaller sample size, you have your population correlation to be significantly different from 0. You have very large correlation, which is 0.6. But if you have say sample size 200, then if you have say around 0. Greater than 0.5, that's the Pearson correlation. That's sufficient to be significantly different from 0 on the hypothesis testing. And then it is important to remember that the correlation does not indicate the causality. So for example, if you have number of hospitals in 50 states, is highly positively correlated with number of household pets in each state. Then if you say the pets, okay, so because we have highly positive correlation between the number of hospital and number of household pets in the state. So number of household pet causes the disease for people, and then we need to make we need to make more hospitals. If you assert that, then it's not correct one, because this correlation cannot be used to talk about the causality. And then for another important assumption for the correlation is each pair of x and y data points is independent of any other pair. So if you have the, say, for one person's the reading and writing score, and then another person's reading and writing score, these two data points should be independent. Otherwise, then we cannot compute the correlation. So let's look at the options in detail. So we have by statement. So as I said, so with the by statement, we compute the correlation separately in each level in this by variable. So for example, if we specify by gender in this this HS Gray data set, so you can see that we have separate correlation coefficient output. So this is for the gender equal to 0, which is the female. So we have 91 or 90 people on this gender equal to 0, and it computes the correlation for females, and then we compute the correlation for the males on here. So that's the by statement. So with statement can allow you compute the correlation between subset of the variables when another subset of variables. So if we specify with statement in here, in the example math and science and social study, so we compute the correlation between this read and write with the group and this group in the specified in the where statement, and then in the group specified in the with statement. So we compute in this example correlation between read and writing and the math, science and social study. So we compute the read and math, read and science, and read and social study. Excuse me, write and math, and write and science, and write and social study. So this with statement is, using with statement, we can calculate the correlation between, and also with the correlation between the one group of the variables and another group of the variables. And so if you look at the another data set for partial in state for partial, let me get back up. So we have a partial statement to control variables to compute the these correlation coefficients. So the partial correlation is the by definition is the we measure the strength of relationship between two variables when the effect of other variables have been removed. So let's look at this example. So we have weight and height and age on here. So we measure the weight and height for 10 students with different ages, and then we can look at that this the correlation. The scatter plot. Then we compute the correlation between weight and height, and then so height, their correlation is 0.93916, which is there is a high correlation between students' height and weight. However, so you can notice that it is possible that there is the effect of the variable age. So this high correlation is due to the effect of the age. So so that we want to control the effect of age to look at the correlation between the height and weight. So here we would like to remove the effect of age and to look at the, I would say that like a pure correlation between, pure effect of the, pure association between this weight and height. So if you look at that, this partial, you can use this partial with the age code. Then if you look at that, then you can see that the partial correlation is 0.48, and then and weight and height, and then this p-value is you can see that 0.1895, which is the greater than 0.05, so which means that there is no significant correlation between height and weight controlling effect of age. So this high correlation is in this example is the effect of age. So we can say that. And then the another options in the partial correlation, that we have the out p equal to option specifies the output data with the Pearson correlation statistics. So you create this CORR_out in this code, then you can print the output on here using proc print. And then another option you can specify is the best equal to number option specify only computes the a limited number of correlation coefficients, and with the ones with the highest absolute values. So if you want to have many variables, and if you want to look at only some correlation, high correlation between the variables, so this is very useful. So you can only limit it. You can make a limit the number of correlation that you get from between variables. Then the order is the absolute value of the highest correlation. So if you have, say, only a specific best equal to 1 on here, then you can only return the highest correlation between variables, which is the highest. And here I specify 2, then we only return the 2 highest correlation for each variable. So which is the so read and math and write and math, and then math and read and science and math, and social science and read. So for pairwise, we have the only return the highest 2 highest correlations. So if you want to specify for more non-parametric correlation, compute the non-parametric correlation, you can specify Spearman, Kendall, and Hofting. For Spearman is Spearman rank correlation. Kendall will be Kendall's tau b coefficient. Hofting reproduces the Hofting's d statistic. So then you can get so if you specify Spearman and Pearson, then you can get both the Spearman and the Pearson's correlation. And then this Spearman and rank correlation also has the hypothesis testing, and then gives the sample size and then the correlation coefficient. To plot the scatter plot, you can use the proc SG plot. So you have proc SG plot statement with the letter scatter statement with x variable for variable in the x-axis, and the y would be variable in the y-axis. Then you have this. If you want to create the scatter plot for all variables, then you can specify proc SG scatter, and you can specify statement matrix, and specify the all the variables in the matrix statement. Then you can get the this scatter plot matrix of the scatter plot. So this is one nice to look at the scatter plots for all the variables, to look at the relationship between linear relationship between the two variables, all pairs of the variables.